Okay, so today is chapters 9 and 10. We're starting chapters 9 and 10. I went ahead and put those together. One is about cellular respiration in animals, one is about photosynthesis. So basically, they're doing the same thing, making energy, but doing it in different environments. And so we're going to be talking about that together. And so that's why I went ahead and put chapters 9 and 10 together. Now, if you want to print out the not the video recordings, I went ahead and put up under your regular lecture notes or lecture PowerPoints or whatever it's labeled, the edited with no voiceovers, no nothing. Went ahead and put up those chapters, so you can get that if you want to print that out, and then as you listen to me talking, you can make edits on your own PowerPoints if you want to do it that way. Anyway, so here is starting chapter 9 and 10. 9 and 10, and the next exam will be after 9 and 10, so after we get done with this. So our next exam is over 8, 9, and 10. So how do we get our energy? How do our cells get our energy? Why do we breathe oxygen? Those are some common questions that you get when talking about cellular respiration. So let's kind of talk about that. So first off, here it is. So the first thing that's going to happen is, sunlight. So this is going to be sunlight coming in. Sunlight. I still can't write very well. And so sunlight energy. All right. So that's going to be sunlight energy. This is going to be kind of a recycle. And this is going to be heat energy coming out here. So first off, we have sunlight. It's going to go into the photosynthesis organelle, the chloroplast. It's going to produce organic molecules as well as oxygen, and then humans are going to breathe that oxygen. Now, the sugars that it produces, we're going to eat those sugars by way of plants or, going through meat and things like that. And then our cellular respiration is going to be happening in the mitochondria of our cells. Now, that's going to be producing ATP, and it's also going to produce a little bit of heat energy. We're going to breathe out CO2. And then we'll also release some some water. And then those are just going to go right back into the building of a plant so that it can harness that sunlight, make more energy, and the whole thing begins again. Ooh, okay. Didn't know that happened. Okay, so the overall reaction for cellular respiration is C6H12O6. And so this is, whoops, I did it again. I don't know how it does that. So this is glucose here. We have 6 oxygens, which is going to give rise to 6 carbon dioxides and 6 water, and then some energy off of that. And so when we look at photosynthesis is going to be the exact same equation, except it's going to go that way. So we're going to start off with 6 CO2 plus 6 water, and that's going to give us carbon dioxide, glucose and oxygen. But right now, we're just going to focus on cellular respiration. So about half of the energy from glucose is collected in ATP. This reaction is highly exergonic, which means it's going to give off some heat. It's a spontaneous, and it drives the endergonic, the non-spontaneous formation of ATP. And so we're going to see that at the end of cellular respiration. We're going to see how all of this is going to be coupled together. 3 basic metabolic processes are used in the breakdown of glucose for energy. First off is glycolysis. And so if you break this down, glyco means sugar, and then lysis, again, I can't write, and lysis means break down. Okay. So we're going to break down our sugars, then we're going, and specifically glucose, and then we're going to talk about cellular respiration, and then we'll talk about fermentation, which is basically breakdown of sugars, an incomplete breakdown of sugars without any oxygen. So cellular respiration requires oxygen. So here we are. This is it in a nutshell. And so all of this, this is going to be all in the plant here. And so all of this is going to be in the plant, and then all of this is going to be in the animal or bacteria. And so the glucose is going to be used. We're going to get the glucose from the plants, but the plants are going to be making the glucose from photosynthesis. Once we get to glucose, then it will just be decided, do we have oxygen? If we have oxygen, then we're going to go to the aerobic process, which is cellular respiration. And that's going to include the Krebs cycle, the electron transport chain, all of those different types of things. If we don't have oxygen, then we're going to go into the fermentation route, where we do not include the Krebs cycle, we do not include the electron transport chain. Instead, we don't have oxygen, and so fermentation is what we're going to do. You get some fermentation byproducts that you don't normally get when you do cellular respiration. So sometimes it's better to do fermentation than doing cellular respiration. So the first thing we want to talk about is a very, very specific reaction that certain enzymes can undergo. And this is the way that the electron transport chain works. This is the way that electron carrying works. This chemical reaction, it transfers electrons between reactants, and this is called the oxidation reduction reaction. These occur together. They will not occur apart. So we refer to them as redox reactions because they always occur together. So we have the reed right there and then the ox right there. In oxidation, the substrate is going to lose electrons, or you can also say it has been oxidized. In reduction, a substance is going to gain electrons or hydrogen atoms. Or you can also say it's reduced. Basically, it's talking about the amount of positive charge is reduced. And so we have a mnemonic to help us remember this. And so oil rig. Okay, so oxidation is loss of an electron, and reduction is gain of the electron. And so this is one way to kind of keep it in your mind how it goes. So oxidation is loss of the electron, reduction is gain of the electron. So oil rig. So if we look at sodium and chloride, so if it becomes oxidized, and so if you're becoming oxidized, remember that means that you're going to lose an electron. And so if you lose an electron, that means you're going to have an unpaired hydrogen or an unpaired proton. And so that's going to give you an overall positive charge. Okay. Chloride or chlorine, this is going to become reduced, which means it's going to gain the electron, which means you're going to have an unpaired electron. Okay, so that's going to give it the negative. And so another thing you can think about is, no, let's just leave it at that. So, you think about the oil rig, and if it gains it, then you're going to have a negative charge. If you lose it, then you're going to have a positive charge. Okay. So during cellular respiration, the fuel that we use as glucose is oxidized, and then the oxygen is reduced. So the glucose is oxidized into carbon dioxide, and then the oxygen that we breathe in is going to be reduced to water. In cellular respiration, I forgot. Oops. Yep. Oh yeah. And remember also that we're going to get plus NRG from there. Okay, sorry about that. All right, so in cellular respiration, the glucose and other organic molecules are broken down in a series of steps. And so glycolysis is broken down in one, we call glycolysis is basically a pathway where you have steps that are you have a little bit of a change in between each step. So you have an enzyme that comes in and brings phosphates, or it takes phosphates away, or it brings in electrons or takes electrons away. And so this pathway is the first thing. So electrons from organic compounds are usually first transferred to NAD. And so NAD, and this is if it's the positive, so that means that it's going to be oxidized, so it has lost an electron. NAD plus is a coenzyme, and so when you have the NAD plus, it's looking for an electron to make it equilibrium, make the positive and negatives work out. As an electron acceptor, the NAD positive function as an oxidizing agent during the cellular respiration. And so what that means is that it's going to accept electrons. Okay, so it's going to accept electrons and carry them away. So each NADH, which is the reduced form of NAD plus, represents stored energy that is then going to be tapped later in the whole process to synthesize ATP. Okay, so if you think about it, you have to remember that every time you have an electron, okay, each electron has a negative charge, is always going to travel with a proton. And so remember, a negative and a positive, that's going to be neutral. So this is going to equal 1 hydrogen. Because if you look on the periodic table of elements, 1 electron and 1 proton is equal to 1 hydrogen. Okay, and that's where you get this H from. Okay, so just kind of keep that in mind as we go through there. The coenzyme NAD, which stands for nicotinamide adenine dinucleotide, it's essential. You will see it all the way throughout glycolysis, the Krebs, and the electron transport chain. It is an essential electron carrier in cellular redox reactions. And so as we are making as we are making ATP, NAD is going to exist in an oxidized form, which is the NAD plus, and then it's going to accept electrons and a proton to now become NADH. Okay. Whoops. So the reduction reaction requires an input of energy. So that's going to be your endergonic reaction. And so the oxidized form, you're going to have NAD positive plus the 2 hydrogen. And so when it's reduced, you're going to get NADH plus an extra proton. So this is going to be a proton. Well, you can't read that at all. Let me do this again. Proton. Okay, so that's going to be the reduced form. The oxidation reaction is going to release energy, which is going to make it exergonic, to go back to its oxidized form. Then you're going to get NADH plus the proton plus the oxygen that is dissolved in your cytoplasm, and that's going to oxidize it back into the original form, which is NAD positive, which is the oxidized form, plus, and there you have your 2 H's.